drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by Edipedia World. Previous lecture I introduced you the concept of kinetics which is involved during phase transformation. We saw that the phase diagrams does not take kinetics into account, but in reality every phase transformation requires certain amount of time. So we introduced ourselves to that idea. Today we'll see some alternative type of diagrams that is used in order to identify the amount of phases that will be formed in reality, and if there is different phase formed, then what will be the different phases formed. This type of diagram, one of those diagrams is known as TTD diagram. Now what does TTD diagram stand for? TTD means time temperature transformation, or alternatively it is also called as isothermal transformation diagram. Let us see the terminologies involved. Time temperature transformation. So basically we are talking about transformation but taking into account the time, that is the kinetics, and the temperature involved. Okay, the alternative name says isothermal transformation diagram, which means that this type of diagram deals with isothermal condition, that is the temperature is maintained constant throughout the transformation. Isothermal transformation diagram. But if you come to think about it, isn't it similar to phase diagram where you have equilibrium? Equilibrium means you are actually giving sufficient time for it to attain a particular temperature, right? It is similar in that sense, but the fact that here in TTD diagram we actually involve the time factor too. We actually provide the amount of time that the material is maintained at one temperature. In phase diagrams we assume that time was not a factor, that at any moment equilibrium is established. Okay, so with this background, let us see what exactly is the TTD diagram. TTD diagram looks something like this. This looks nowhere similar to the phase diagram. So let us understand all the different components involved here. This axis is time, and it is plotted in logarithmic scale, because if we do not take log, then the effect cannot be observed. Then the curve will be really elongated, and as we saw in the previous previous lecture, that the Abrahami relation is an exponential relation of time. Therefore we require a time component which is in logarithmic scale. This axis is our temperature axis. It can be in degree Celsius, it can be in degree Fahrenheit, doesn't matter. Now let us consider the eutectoid composition itself. Just to remind you, what was the eutectoid composition? It was gamma here, transformation taking place, ferrite plus cementite at 727 degrees Celsius, and this composition was 0.76% carbon, right? This was the eutectoid transformation, and this was the phase diagram representation of it. But in the TTD diagram what we do is that we draw the eutectoid temperature, which is 727 degrees Celsius, and then these curves shows the actual start and finish of perlite. This is the perlite start curve, and this is perlite finish curve. What does this mean? This means that ideally austenite should be present only till 727 degrees Celsius, right? Below that we should instantaneously have perlite if we go just via phase diagram, but in reality kinetics needs to be taken into account. So let's say that we start the time we start from 800 degrees Celsius, we cool it down to, let's say, 700 degrees Celsius very quickly, and now we hold it at 700 degrees Celsius. We hold it at 1 second, still we have 100% austenite. We do not have any perlite till now. We keep it at 700 degrees Celsius. At 10 second also perlite hasn't started to form. At 100 second perlite hasn't started to form. Finally over here, which is somewhere might be around 500 seconds, perlite starts to form. This is perlite start curve. Till this moment, everything which we have was 100% austenite. We did not have perlite. Here perlite starts to form. Okay. Beyond that, let's say we are over here at 1000, almost 5000 seconds. We have attained only about 50% perlite. So even at this location, we are 50% perlite and 50% austenite. In order to get 100% perlite at 700 degrees Celsius, we need to maintain the temperature for really long time. As you can see, even at 10 to the power 5 seconds, it is not cutting the 700 degrees Celsius isothermal line, is not cutting the finish curve, perlite finish curve. That means even at 10 to the power 5 seconds, that is more than 1 day, we do not get 100% perlite if we maintain 700 degrees Celsius. Okay, so you see how different is it from the thing which we saw in the phase diagram. Phase diagram just assumed equilibrium and instantaneously you had perlite. But here at 700 degrees Celsius, which is actually a undercooling of 27 degrees Celsius, you do not get 100% perlite even after one complete day. Now alternatively, let's think that we take it down to 600 degrees Celsius. Then perlite starts forming at about 2 seconds. And perlite is completely formed. 100% perlite is formed before 10 seconds. Okay? See the interesting thing here. At 700 degrees Celsius, 1 day was not sufficient for 100% perlite formation. At 600 degrees Celsius, under 10 seconds we get 100% perlite. So that is the power of TTD diagram. It, in a very concise diagram, packs a lot of information, a lot of heat treatment information. Okay? And TTD diagrams are drawn in such a way that these lines are actually based on isothermal transformation condition. So you cannot continuously keep cooling. You need to hit a particular temperature and maintain that temperature. That's why isothermal. But in reality, that won't be always the case. There will be cases where there will be continuous cooling. For that, we'll discuss in our next lecture something known as CCT diagrams, continuous cooling transformation diagram. But for now, we assume that we are in the heat treatment categories where the temperature is maintained isothermally. Okay, so just to recap, this was perlite start, this was perlite finish. Anywhere in between you have certain amount of perlite formed and remaining austenite over there. Then again, you might ask, why is it that the kinetics is so slow at high temperature, and why is it that the kinetics is so fast at lower temperature? Shouldn't it be the opposite? Shouldn't it be that at higher temperature you have higher diffusion rate and the kinetics should be high? That is, the perlite formation should be quicker. Okay, so just to give you the idea, there are two competing processes here. Rather, there are two steps involved, as we discussed beforehand. One is nucleation and second is growth. As I said previously, for nucleation you need undercooling. You need to have a driving force. Undercooling. Less the undercooling, more nucleation will take time to occur. Growth, is diffusion based. So for growth, higher temperature, faster the process. So what exactly is happening here is that nucleation is kind of the deciding factor in how much time it will take. The nucleation of perlite is taking a lot of time at higher temperature because the undercooling is quite less. At 700 degrees Celsius we have 27 degree undercooling, whereas at 600 degrees Celsius we have 127 degrees Celsius undercooling. This perlite formation takes place till around 550 degrees Celsius. We will see what happens below that later. So at 550 degrees Celsius we have an undercooling of 177 degrees Celsius. So what we see is that as we lower the temperature and as we approach 550 degrees Celsius, the undercooling increases, thereby nucleation does not take much time. Okay, and though the growth is diffusion focused, the deciding factor is diffusion, still 550 degrees Celsius in itself is a quite high temperature. So the diffusion rate does not vary drastically between 550 degrees Celsius and 700 degrees Celsius. So basically growth does not take a lot of time. Nucleation takes most of the time. Therefore, higher temperature requires a lot of time to form nucleus, thereby the process of perlite formation takes a lot of time. Lower temperature, nucleation driving force is much more higher, nucleus are formed immediately, diffusion is still quite high rate, thereby the perlite formation is quite rapid. Fine. So we see that using the TTD diagram, not only can we predict at what time we will have perlite start, at what time we will have perlite finish for different temperatures, but also we can predict at any intermediate time what percentage of perlite is formed and what percentage of austenite still remains in the system. Okay, with this background, let us see something more now. I just discussed that we have perlite formation up till around 550 degrees Celsius, right? But there are actually two types of perlite. If you remember from previous lectures, perlite is basically a lamellar structure with alternating layers of ferrite and cementite. So you have ferrite and you have cementite. And we know that ferrite is to cementite ratio of width is 7:1. But the cementite can be 1 micron and ferrite can be 7 micron, or the cementite can be 10 micron and the ferrite can be 70 micron. The ratio needs to be maintained, but we do not know each of them is how thick. So it can be really fine, it can be quite coarse in structure. How do we find out, or what decides whether the perlitic structure will be fine or coarse? Okay, that is decided by what temperature we are holding and trying to form the perlite. It is basically depending on the isothermal hold temperature. Let's again assume two temperatures, like at 700 degrees Celsius, what is happening? We have a lot of a very high temperature, thereby diffusion can take place over large range, large distances, right? But the number of nucleus formation is quite slow. Formation of nucleus is very less because of low driving force. Thereby the number of nucleus formed will be less, but the diffusion rate, possibility of diffusion is more. Therefore what happens at higher temperature is that we get coarse perlite, because we have less number of nucleus, and the diffusion of carbon from ferrite region to cementite region can be easily done. Therefore they can be separated by larger distance, thereby we have coarse perlite. But at lower temperature, what we have is that we have a lot of driving force. Many nucleus originate, thereby the nucleus are quite close to each other, and that added to the fact that diffusion is slower at lower temperature, we have fine perlite at lower temperature. Fine perlite. Okay, so this gives you an idea where we will have a coarse pearlitic structure and where we will have a fine pearlitic structure. We'll not go into the details of exactly how the property varies between coarse and fine perlite. We'll see that briefly later. Now, the previous two diagrams which we discussed, we were discussing about the Eutectoid phase, Eutectoid composition. We were discussing about 0.76%. But what if we are at a different region? What if we are at, let's say, 1.1%? Then what will happen? The thing that will happen at that time is, let me draw that region again. This is 0.76% carbon. This is 727 degrees Celsius. Here we have gamma. Here we have gamma plus Fe 3C, and let's say we are at 1.1% here. Okay, then initially we have 100% gamma, that is austenite, but in this region we form austenite plus cementite, that is austenite remains and cementite is formed additionally. This is called as proeutectoid cementite, if you remember. That is reflected in TTD diagram also. What is happening is, you suppose you are isothermally treating it at this temperature, let's say 750 degrees Celsius. So we basically cool it from, let's say, 800 to 750 degrees Celsius, and we hold it at that temperature. Initially till 1 second it is 100% austenite, but at around 3 to 4 seconds what we see is that cementite starts to form. That since we are at this region, we should have cementite, but that cementite formation is also diffusion driven, therefore there has to be a kinetics which leads to this slowdown. And now if we maintain the temperature, we get the cementite, we form the requisite amount of cementite that should be formed over there. This is the proeutectoid cementite. So this region we have gamma, that is austenite, plus proeutectoid cementite. Fine. Now suppose instead of isothermal hold at here, if we isothermally hold it somewhere over here, what will happen again is that obviously there will be some proeutectoid cementite formation before it hits the perlitic formation start curve. This is where the nucleation of perlite occurs for the first time and perlite starts to form. Furthermore, it is the same diagram as before. The only difference here was that due to the hyper eutectoid scenario, we will have the proeutectoid phases formed. This would have been the same if we took a composition over here, let's say 0.5%, then instead of proeutectoid cementite we would have proeutectoid ferrite forming before, but rest of the phenomena would have been on similar lines. Okay, so this gives you an idea about the eutectoid behavior, and we saw that in TTT. We saw the proeutectoid phase formation in TTT also. Now let us see what happens if we go below 550 degrees Celsius. I said you that till 550 degrees Celsius we have the phase perlite formed, rather the combination of phase perlite formed. But if we go below 550 degrees Celsius, then we have a different kind of phase formed, that is known as bainite. Okay, if you remember the phase diagram, there was no bainite in the phase diagram. Okay, this means that bainite is not the most stable phase, rather it is a metastable phase. But being metastable, it has needle-like structure. We'll not go into the details of that. It has a much higher strength and hardness than perlite, and thereby using this heat treatment, when we require higher strength, higher hardness than perlite, we actually form bainite rather than perlite. We do not isothermally cool cool the austenite above 500 degrees Celsius, rather we cool it below 550 degrees Celsius. What we do is this, just to show you, this is the perlite formation isothermal curve. For bainite, you go below 550 degrees Celsius. 550 degrees Celsius is kind of a nose. Beyond that, the kinetics slows down again. Why? Till here, till 550 degrees Celsius, the kinetics was governed by the amount of time taken for nucleation. Below this temperature, the kinetics is governed by rate of diffusion. If you remember, I discussed about nucleation and growth. So this was driven by nucleation, this is driven by growth kinetics. So what we do is we come at a lower temperature and we cool. Similar to perlite start and perlite finish, we have bainite start and bainite finish. We cool it, let's say we are at 450 degrees Celsius. At around 2 seconds we start forming bainite. Till that time we had 100% austenite. At around, let's say 10 seconds we have 50% bainite formation. At around 50 seconds we have 100% bainite formation. Okay, so we see that the driving force is sufficient for nucleation. Now whatever is driving is the rate, whatever is driving the kinetics is the rate of diffusion. So as we further lower the temperature, the amount of time required for bainite start and bainite finish keeps on increasing, because now the diffusion is really getting slowed down. Further down temperature, further more time is required. Okay, so with this TTD diagram we see that we can form either perlite or we can form bainite depending on what temperature we are treating the material. So this TTD diagram is very handy to understand the different heat treatment processes. We'll also see a different kind of phase altogether. Today we discussed about perlite and bainite. We'll see something which is known as martensite, which is not formed by diffusional processes. Martensite is a diffusion-less process, formation of martensite. Therefore, martensite formation is actually supported at quite low temperatures. We'll see that in a later lecture. Hopefully you understood the concept of TTD diagrams and why we need TTD diagrams. With this background, we'll continue our next lecture. Till then, have a great day. Goodbye.